In the next few videos, let's look at the neural tangent kernel or NTK. The idea is that for very wide neural networks, the training process, the gradient descent, start to behave like a kernel method. In fact, the entire training dynamics can be described by the kernel matrix for the training dataset. So today, let's look at how the NTK arises from gradient descent. So let's start things simple because it is not really specific to neural network. So for this video, we'll just look at the linear model and the nonlinear models to see how the idea of NTK emerges. Then for the next video, we'll look at the neural networks and the neural tangent kernel. Then after that, we'll zoom into the spectral property of the kernel matrix, which can provide us insight into modern neural networks and AI models. In order to understand how neural tangent kernel arises from gradient descent, let's first look at the easiest possible example here with linear models. So suppose that we have n data points, x and yi, and then we also define some feature map from x to phi of x. So I should say that this linear model is defined in the feature space. It's not in the input space x, but in the feature space phi of x. So here it means that our nonlinear function, we can define f of x as phi of x transpose beta. So that's a linear function in the feature space. Then for the objective of the linear model, we just minimize the squared loss, right, between the y, and then this is the f of x at all the data points. And here everything is written down in the matrix form. Let's just spell out the dimensions. So y is n by 1, phi is n by m. So feature space is m dimension, suppose. Then the beta is m by 1, right? Okay, although this problem is quite trivial to solve, we can do it with normal equation, but let's just use gradient descent in here. So now let's just consider solving this with gradient descent. So the first thing we can do here is just to compute the gradient for the beta vector. So the gradient of L beta, that equals to minus phi transpose times 2 times y minus phi beta. Then we can just plug in the gradient vector into a gradient descent formula. So we'll have the update rule as beta t plus 1 equals to beta t minus a learning rate, let's call that eta. And then we can remove some constant in here, right? The constant 2 can be removed. Then we will have phi transpose phi beta minus phi transpose y. So that is a gradient descent formula for the linear model. Okay, I should say this beta is beta t. In order to see how the kernel trick pops up, let's just multiply both sides by the phi matrix. Okay, I should say that the kernel matrix K equals to phi transpose, right? So that's the kernel matrix. Okay, so we're just gonna use phi to multiply both sides, and then we'll have phi times beta t plus 1. I'm gonna move the beta t to the other side, minus phi times beta t equals to eta. I'm removing the negative sign as phi transpose y minus phi transpose phi beta t. Okay, so here we can actually plug in the expression to replace all the phi, right? Because you see here that phi times beta equals to the function f, right? So we can replace that with the f of t plus 1. I should say this is a f hat because it's a predicted value minus f hat of t equals to eta times ky minus k times f hat of t. Okay, so see this equation here, right? For the left-hand side, This is an update of the predicted value of the step t, right? We run one gradient descent step, then we update our predicted value from ft to ft plus one. So I can write that as a delta f hat of t, right? So this is the updates for step t. And then on the right-hand side here, I have eta times k times y minus f hat of t. Okay, so for the right-hand side here, right, this is y minus f hat of t. This is a residual for the step t. So I can say this is a residual of uh, of the t step, right, of our predicted value at the t step. So here the interesting thing is that for our update at the t step, it is a linear combination for the kernel matrix K here, right? So it means that we are updating in a subspace of the data. Okay, so here's how we can think about this problem for the gradient descent. Okay, so this is a geometrical picture you can use to interpret gradient descent. So linear regression can be thought of as a projection of the vector y onto a subspace defined by the feature phi here. Then the gradient descent, because according to this formula, it's just saying that it stays in this subspace the whole time during the update. So suppose we are starting with some initial values f of 0, then each step is just going to move along in this subspace here according to the residual, right? So the residual can be drawn as a vector from x pointed to y, right? So that's going to be the residual r of 1, right? Then we kind of use this matrix K here to move this residual vector into the subspace and then make our update. Okay, so in order to understand a little better about this picture, let's just quickly apply an SVD formula on the matrix phi to see like how, what exactly is this subspace, right? So we can apply SVD on the phi matrix as U sigma V transpose. And then we can also spell out the dimension for this problem exactly, that U is an N by D matrix, sigma is a D by D matrix, and then V transpose is a D by M, right? Matrix in here, right? So see here that because our F, right, our F is can be written as phi times beta, right? So that equals to U sigma V transpose beta. And when we have formula like this, right, it means that the F is a linear combination of the first matrix U here, right? So that is really our subspace, right? So instead of phi here, we can also write it, think about it as a bunch of singular vectors U, right? That's U1, U2, right? So that defines this subspace. Then for our matrix K, right, K equals to phi transpose, that's gonna give us U sigma square U transpose, right? And then when we use K multiplies by the residual RT, that also lives in the span of the singular vector U, right? The reason is because we have U as the first matrix here, right? So that means the update always lives in this subspace defined by the singular vector U's. Okay, so this is really the key intuition for the neural tangent kernel, is that during the gradient descent update, there's a subspace K that defines where all the update happens. So the entire training process taking place in that subspace, regardless of the dimension for the phi, right? Phi, you see that phi is an n by n matrix here, and depending, in some cases, like when we have a very large neural network, m can be very, very large, right? Depends on number of the parameters we have. But it turns out that the gradient descent doesn't care about that, right? It only care about it's only care about this kernel matrix K here, right? So that's an n by n matrix given by the number of training data points. That's where all the training steps when the update occurs. So next problem, we're going to look at a nonlinear function. That's where the NTK, the neural tangent kernel, starting to emerge, right? For this problem here, although we are having a feature map, the phi of x, where that's help us with the non-linearity for the problem, but technically it's still a linear problem defined in the feature space, right? But for the next problem, we're going to look at the true nonlinear case. Okay, so let's do that. Then for the second problem, let's just look at the general nonlinear function fx beta to see how the gradient descent formula gave rise to the neural tangent kernel. So this is our objective function here. We're still going to consider the squared loss. So L is a loss function. Right, then maybe for the next example, we can look at the general loss function here. But for this example here, let's just look at the squared loss first. Then the function f here is just going to be a general nonlinear function, right? A good way to think about it is just going to be you can just think of this as W transpose beta plus B, and then use some activation function sigma to transform it, right? So that's can be a way to define x. So this is something we commonly use in neural networks. We just do a linear operation first, and then use some nonlinear function, activation functions such as redo or sigmoid, to transform the output. Okay, I think here it should be x instead of beta. So that should be x, right? And then our beta is weight and the bias, right? So it has two parameters. Also you can just think of this problem as a neural network, right? Because the way we can draw it is that you have the input x, right? And then we just multiply by the weight vector, right? Right. We just multiply it by the weight and then plus b, and then we pass this output through a activation sigma, right? So that's going to be the output. And then for the linear models, right? For linear models, the sigma is just going to be the identity function, right? So that can also be thought of as kind of a one layer neural network, right? So this is a one layer neural network if you think about this way. Okay, so now let's just take a look at the gradient descent for this problem. So gradient descent. So the first thing that we can do here is just to compute the gradient. So the gradient vector, and then we can apply the chain rule in here, right? So the chain rule, so first we'll have the Jacobian matrix. So that's gonna be the Jacobian matrix of x beta, and then you need to transpose that. Then we can multiply that by 2 times y minus f x beta. Okay, now for the update rule, we have the beta at t plus 1 step equals to beta t minus eta times the gradient. So gradient, we can move this negative sign inside, right? So we have jf x beta transpose, and then we have f x beta minus y. Okay, so now this is the difference between the derivation here and the derivation for the linear models, right? Because we can now just multiply by the matrix phi here to get the predicted value. But what we can do here is just to apply the first order Taylor expansion to see what happens, right? So the first order Taylor, that's going to give us f hat of the step t plus 1 minus f hat at step t equals to the Jacobian of x beta times beta t plus 1 minus beta t. Right, so that is the first order Taylor formula. Okay, I should also change this equal sign here to approximate. So we can use a linear function to approximate the difference between the predicted value. Now we can just multiply the Jacobian matrix for both sides of the equation. Also, what we can do here is I'm just gonna move the terms a little bit, right? So I can just move this beta t to the other side, right? And then it means that I can just change this to a minus sign here, and then that equals to and then also I'm just gonna change this I'm just removing this minus sign here, and then I'll revert the last term, right? Just become y minus f. This is going to be y minus f x beta. Okay, now we can just multiply both sides by the Jacobian. That's going to give us f hat t plus 1 minus f hat of t. That is approximately eta times jf. Okay, so this is the equation we got in the end, right? So you see that this equation looks a lot like the linear case. So we can actually define this Jacobian times Jacobian transpose as a kernel matrix K. So this is the definition of the neural tangent kernel. To see why this is a kernel matrix, right? It's worth to expanding everything out. Um, so So actually, we'll see that the entry in this kernel matrix will be the inner product of the gradient vector for each training data points. I should probably just spell the dimension first, right? So the beta, that's going to be an m times 1 vector, right? And then for the f, the predicted value here is an n by 1 vector, right? It means that our Jacobian here is going to be an n times m matrix, n by m matrix. Okay, so at least the dimension you see here is correct, right? We have n by n matrix for the kernel. But let me just spell it out. Okay, so now I have spelled out the entire matrix for the Jacobian and the kernel matrix. So the Jacobian matrix contains all the gradient vector from the first data point x1 to xn. So that is why the dimension of it is n by m matrix, right? So if we just further expanding it, it will just have all the partial derivatives for the first data point with respect to the first parameter to the last data point with respect to the last parameter, right? So that is Jacobian matrix. And then when we take the J times J transpose, it will give us the inner product between the gradient vector for each pair of the training data point, right? So here we'll have, for example, in the first entry, we're just going to have the inner product between the first data points with itself. So see here that one thing is that we can't really get rid of the dependency for the step t in here for this Jacobian unless this is a linear function, right? So that does not depend on the beta vector. Otherwise, it's just gonna have the dependency on this beta, right? So that means we cannot have an adaptive matrix K that changes in each training step t. But you see here that this dependency on the training step t for the kernel matrix means that there is not a single subspace our gradient descent lives in. But for one type of the neural network, if the neural network is wide and over-parameterized, so when the neural network is wide and over-parameterized, then we can actually approximate the kernel matrix at each step t as the kernel matrix K, right? So that means the kernel stays constant. This particular network is what we're going to look at the next time. Okay, so the last thing I want to say in this video is that what happens if you have a loss function in general, not just the square loss. Okay, now for the general loss, we're just gonna write it as the L as with respect to y and then f x beta, right? It doesn't have to be squared out. So the only thing that we need to replace here is this term. This term here coming from the derivative uh, of L with respect to the function f, right? So when we have kind of a when we have a loss function in general, we're just going to replace this term with this derivative in general, right? So that's not going to change too much for this problem. So we still have the same kernel dynamics for this problem, except that we cannot interpret this problem with a residual anymore, right? So that's the only difference we're going to have. Okay, so that's pretty much about this video for the motivation of the neural tangent kernel and the gradient descent. Then for the next video, we are going to look at the wide neural network to see why we can approximate the kernel matrix with a constant, and then how does that govern the dynamics of the training process for the neural networks.